in this first half hour, we're going to originally, for this first half hour, I'm going to ask you to use your imagination and imagine that you're in a room of only 10 people and you're all working together on your computers and you all have good internet and you're all working through actually using our protocols. As it turns out, none of that is possible because we don't have internet, and also it's pretty tricky to do this on a setup like this. So instead, I'm going to be talking to you about the protocols. It's very exciting. Cool. So let's talk about BitSwap. There's going to be a lot of talk about BitSwap in this hour. Feel free to tweet about it. Is that a thing? Yeah. Give your thoughts. So what's BitSwap? Well, here's BitSwap, the protocol. Very obvious, of course. BitSwap is a block request protocol. It means that BitSwap is a protocol for asking for blocks based on SIDs. Very straightforward. Sort of, again, that minimal basis for working with content address data. And the way BitSwap works, you can see these like little, okay, this is a protobuf, but, and I know that's a little complex and codey and you maybe can't read it, but basically it has two sections. One is want list, which is basically the blocks you want. It's essentially a list of SIDs. There's some complicated things around what you want to know about those SIDs as the protocol's developed. And then you have a series of blocks. So basically you can either want, or you can get stuff, or you can get it back. Interesting thing about this, if you look at this message format, it doesn't really look like a protocol that's a request response protocol. It looks like you can be both sending wants and getting blocks in the same message. And that is in fact the case with BitSwap. BitSwap is more of a pub sub protocol, which is interesting. It creates some interesting problems and challenges. So one key thing I want to say about BitSwap, it's so key that it doesn't appear on the slide. And that's, sorry, this is a mistake. Anyway, that is that a protocol is not the same as an implementation. So I showed you that little protocol slide, and that is the BitSwap protocol, but the implementations of BitSwap do a whole lot more. And this is an ongoing source of confusion, is that people will look at Go BitSwap, or now Rust BitSwap, maybe even JS BitSwap, and they'll say, oh, well, that's just BitSwap. But actually, they're doing way more than BitSwap. They're, in fact, doing a number of different things that are key to the entire process of getting content on IPFS, like content routing, which is what we talked about this morning. Anyway, so I just want to make that clarification. If somebody says BitSwap, you can ask, do you mean the protocol or the implementation? And you'll sound, hopefully you will not stump them. If you stump them, you'll know they don't know what they're talking about. Cool. So we talked a little bit about IPLD and how it's made up of these blocks that link to each other. And I don't know if Mav mentioned this word MERKLEDAG, but I wanted to bring it up. MERKLEDAG means essentially a tree of blocks that are linked together. It's a bunch of blocks that are hashed, and inside of the block content is links to the hashes of the other blocks, right? And so let's talk about how you would synchronize a MERKLEDAG, right? If you are trying to do incremental verifiability with BitSwap. Again, remember, you don't want to download everything and then find out you have the wrong thing much later. So the interesting thing about this is you can imagine if I started with the root block, right? Inside the root block are the hashes of the blocks immediately below it. So that means that I can download the next layer of blocks. Let's say I traverse over the left side, and I get the first block at layer 2, right? And when that block comes back, it comes back as a bunch of bytes, and I can rehash it and check that the hash of the data I actually got matches the hash of the data I requested. And that's how, again, you do this verifiability, right? And then once I had that, I could look at the data in that layer 2 block, and I could say, what are the hashes that are inside this block? And that would tell me about layer 3, right? That would tell me where to go to get layer 3. And now I can request, maybe I go down another way to the left, and my second request is for the far left block at layer 3. And then I get the next block at, to the right. And now I'm all the way back up at the top, and I start going down to the right, and I ask for the second block at layer 2. I get the hash back, I get the block back. I verify it. I look at its content. I get the hashes from that content to the third layer on the right, and then I traverse those, right? So that's actually a relatively complicated process. You might, does anyone know what the problem with this process is from BitSwap standpoint? Like why it might be slow? Yes. What? Round trip, yes. So I don't know the hashes of the stuff at the bottom when I start, right? So I have to get the first block in order to go to the next level. And that means I'm looking at, just for this simple DAG, maybe 3 layers of round trips just to get the content. And if you've worked on the internet, you know that a round trip is like a huge penalty. It's like 100 milliseconds of pause, which is terrible in good cases. You can imagine, though, that the one nice thing about being a block protocol is that if my DAG happens to be super wide, right, I can request both of the second layer in parallel, because I know both of them, and then once I have them, I could go right to requesting the entire bottom layer at once. Because again, BitSwap can request lots of blocks at once, and it can request and download them from many peers, right? Where BitSwap excels is the multi-peer, and so this is wonderful because I can basically really only have 3 requests, 3 rounds of requests to get everything. Unless I'm syncing something like a blockchain. And there's no way to avoid the round trip problem here, right? You essentially have to step down each layer with a round trip, and that leads to a slow transfer. So let's talk about our other protocol, which attempts to remedy some of that. Let's talk about GraphSync. So BitSwap is the original IPFS data transfer protocol. It's seen a lot of work, a lot of evolution. You'll hear from someone who literally just re-implemented the whole thing in a moment. And GraphSync is now, I don't know, it's like I feel like where if BitSwap is like the senior citizen, now like GraphSync is like the middle-aged person. It's not quite a young upstart anymore. Basically, GraphSync is an attempt to write a data transfer protocol that doesn't understand blocks, but rather understands DAGs, understands IPLD, so that you can ask other peers not to send you a single block, but to send you a whole DAG back. And this essentially addresses the round trip problem. What it does mean is that GraphSync has to understand data at a much more complex level than BitSwap. It has to, in order for 2 peers to communicate over GraphSync, they have to understand almost all the aspects of IPLD. This includes codecs, blocks, the data model, even schemas and ADLs in some cases, right? And I don't know if you all remember if we go back to the opening presentation, one of the big challenges is making sure that both sides understand the same complex data model. And we get into a lot of problems with this if the sides don't have quite the same implementation. It makes it complex, right? GraphSync allows you to express queries against IPLD data using something called selectors. Selectors are essentially a query language for IPLD. I don't know if Mo covered it in their talk, but you did. Yes. Sorry? No, maybe not. Okay. Oh, cool. So this is new. You can imagine selectors as a way of expressing a full or partial traversal of an IPLD graph. You can imagine, if you imagine this sort of like DAG image here, and then you look over here on the right, you can see like the green one, you can imagine that as a path selector, essentially saying, I want you to traverse a series of nested nodes or blocks or whatever that are on certain named paths. And this makes sense a lot for like directory traversal. You might also say something like, I want you to traverse a series of nodes via a path, and then once you get to that path, I want you to give me everything underneath it. It's quite a complex query language, probably too complex, but it does a lot of stuff. I know there was a request for maybe there's a better replacement for BitSwap, and I would say possibly under certain conditions. One is that you do need to do complex queries and have them be pretty fast, end-to-end over a single peer. GraphSync's Achilles heel is that it is primarily a single peer transfer protocol. It's very hard to think about splitting up DAG requests without knowing anything about the DAG ahead of time. It is, at this point, pretty tested, and I would encourage, one reason you might want to do it rather than rolling your own is there might be some complexities that you don't yet know if you haven't tried to re-implement something like this. So it's there. And finally, if you happen to be using Filecoin, well, you used to have to use GraphSync, but not anymore. There was a talk here yesterday about how you can now use BitSwap. It's very exciting. Cool, all right, but these are amazing protocols, GraphSync, BitSwap. But we've got one more thing. That's right, this is amazing stuff. Right here now, folks, we are introducing a revolutionary new data transfer protocol. This protocol is set to disrupt the IPFS world and auto-magically upgrade our transfer speeds, and we're releasing it here today on stage, because everyone loves an on-stage release. Woo! Okay, here's what we call it HTTP something or other. It probably doesn't work at all, but it might. And it's new, and new is cool. So to talk to you about how to introduce a new protocol to IPFS, we've got Will Scott, my coworker.
I think this is really more mad science than trying to talk about something practical or something that we're actually going to use. But really what we wanted to talk about is that we have extensibility now. And we're moving to a world where we should be able to think about a lot more extensible data transfer protocols than what we've had. And so I think there's a number of things. Probably most excitingly is the IPVM and thinking about shipping code to another node rather than just data. Because then I can ship code that causes it to understand some new protocol and continue to evolve protocols in the way that make the most sense. So what would we need if we wanted to add another protocol? And we'll use, for this example, HTTP as a thing that we might want to be able to support. The first step, as we covered for most of the morning, is content routing. We need to learn that there's a provider that has content address data that would be compatible, that we could actually try and get. I'm not going to try and do internet things on the stage, but you can follow along at github.com/willscott/http-sid-data, which is a little GitHub repo that has some blocks in it. And so you can see it as a GitHub Pages hosted repo where there's a directory, and you can say, thing.github.io / and then a SID, and you'll get the block that hashes to that SID back. And OK, so this is a scheme that we can come up with. This is very simplistic. But that is sort of like BitSwap in some sense, except over HTTP. I'm asking for a block. I get back the block if the server has it. So if you take that as your provider, how would you then learn that this provider exists and for what blocks? Network indexers allow an index provider, someone who has content, to announce that content in one of two ways. Either over libp2p, which is how many of our providers are announcing it, but also over HTTP. And so we have some providers, like NFT Storage, for example, who maintain an S3 directory where they keep their list of all of the SIDs that they have, and the indexers slurp that. And so in this repo, you'll also see that, and you'll see a README for how you could generate that yourself. But you make an advertisement as another file that's named as its SID that says the set of SIDs that exist in that directory. And then you can tell the indexer, hey, this exists as a provider, and it's able to parse that and index the set of SIDs that it should return a record saying those SIDs are available in this directory. I think I described that very simply. And the reality involves a lot more fiddling with things. But it's conceptually not that hard. I think the thing that you should focus on is not those mechanics, but rather what sort of additional protocols would you want. So asking for a single block can work. It looks a lot like Bitswap in terms of round trips. I make a request, I get a block. But what about car files? We could potentially make a request for a car file, like you already do on the IPFS gateway, where you ask for a DAG export and get a whole streaming set of blocks back. This is also incrementally verifiable. So there's a whole class of additional data protocols that we can imagine that are not going to be that hard to add in. And the real trick is going to be figuring out the IPVM layer and what the interfaces are to allow another IPFS node somewhere else to start trying and being able to iterate and have different logic in how it does data transfer. How many of these slides are there? Cool. So OK, so you define your transport format. I misused the HTTP multi-codec as the number of the metadata that I say that it is. So this looks like HTTP, which causes many people to be unhappy at me. The multi-adder, I added a new multi-adder component called HTTP path, where I can then say it's actually in a subdirectory. We don't have that in multi-adder. That means JavaScript multi-adder crashes because it can't handle new types of codecs or new multi-adder sub components and doesn't have an extensibility. So we'll need to work on that. We told the indexer, and then we have a client that can fetch it. There's an experimental client in IPFS Shipyard called the Web3 Retrieval Client, W3RC. And there's a branch there that is able to understand this additional record that it gets back and make an HTTP request. So I will turn this over, but I will say again before I do, the URL, github.com/willscott/http-sid-data. And you can see the different steps that you go through to experiment with adding additional transport protocols.